Walter, yes.
Can we do the first problem on the quiz?
The first problem on the quiz, 1, 2, 1, 4, sure. Okay, so if you're just asked to write 1, 2, and 1, 4 products, you want to go ahead and just choose an end because it's symmetrical. So we would choose 1, 2, 3, and 4. So if I'm just writing the products, I would write the H adding to carbon 1, and then the Cl adding to carbon 2. So that's the 1, 2 product, and then the H adding, and H and Cl adding to carbons 1 and 4, and remember the double bond moves between 2 and 3. So those would be the two products, the 1, 2, and the 1, 4. Tom?
Do we have to explicitly say where we put the hydrogen or not?
No, I mean, no, if the hydrogen's not there, then it'll just, it'll look like that if I erase the hydrogen. So no, you don't have to show that, but I'm showing it just so everybody knows where it goes. Okay, so then looking at this, the thermodynamic product is going to be the one that's most stable, which is going to be top or bottom. Thermodynamic, bottom, because it's the most substituted, so that would be the thermodynamic product. And then in theory, the other one should be the kinetic, probably, but we have to double check. So what kind of carbocation did this come from? It came from a tertiary one, a tertiary allylic carbocation, so that would be the kinetic product because that's more stable than, that's going to be more stable than having the plus charge on carbon 4. Sarah?
Like in what kind of situation would the kinetic and thermodynamics be the same?
They would be the same if, or they would, well, there's two situations. They would be the same if they're the same product. So here would be an example where if I do 1, 2, and 1, 4 addition, I end up with only one product. Right, so if we added HCl to this one, we would add H here, Cl there, the double bond would stay there, that's 1, 2, and then H here, double bond moves between 2 and 3, and put the chlorine there. Those two are the same product. So in this case, there is no kinetic and thermodynamic product, there is one product. So I can't change the major product if there's only one product. The other case where you might have multiple products but no kinetic and thermodynamic product would be if you had, let's say, 2 secondaries or 2 tertiary carbocations. Then you would end up with 50-50 and you couldn't reverse it. So maybe an example of that would be something like that, which is unsymmetrical, I know. So you would get 2 different products depending on which carbon you choose as 1 and 2. But in this case, if you added, let's say we add to the bottom, the H to the bottom carbon, we would end up with, bad choice. That's a bad choice. That's a better choice. There would be 1 tertiary carbocation for addition to carbon 1, then its resonance structure would look like this. So in that case, we would get 2 tertiary carbocations, and whether the carbocation's in the ring or outside the ring, it would have equal stability. So in this case, we would get 2 different products, but changing the reaction conditions would not change the percentages of the 2 products because they have the same carbocation intermediate. They also have, the double bonds also have the same number of carbons attached, so therefore they're tied. So those are kind of like the exceptions to the rule. Those are kind of not interesting. Does that help? Any other questions?
Can we see the Diels-Alder again?
Sure.
Stereochemistry.
Which kind of stereochemistry?
We do them like this, like one on one.
Yep. So let's talk about the rules then, and that'll build up to what's today. So rule number one with Diels-Alder rules are that the diene has to be in the S-cis conformation. So S stood for sigma, and there's free rotation around the sigma bond. So in this case, it has to be S-cis as opposed to S-trans, because the way that the reaction goes is for the diene, those are all the all the p orbitals in the diene. Here's the alkene with its p orbitals, and basically they're going to overlap like that, and the spacing has to be such that the ends of the diene system here, those ends are, the ends of the diene system overlap perfectly with the alkene, so it has to be S-cis. That's rule number one, but that's the diene. Then as far as the stereochemistry of the alkene goes, if you have a trans alkene or a cis alkene, the stereochemistry in the alkene is preserved in the final product. So I'm going to end up with a 6-membered ring with the double bonds between carbons 2 and 3. And let me move the 5 and 6 inside. And then these, in this case, the two CN groups are going to be trans. It doesn't matter whether it's bold dashed or dash bold. The key is that they are trans with different wedges. So the stereochemistry of the alkene transfers to the stereochemistry of those two groups in the final product. And the reason for that is because the diene basically comes in and plops right on top of the double bond. It's not like it forms one bond and then the alkene can spin around. It forms both bonds at the same time. So whatever the alkene stereochemistry was, it gets locked into the final product.
So I think on the problem set, there was like 2 like rings. So I'm just not sure, like, does it matter which one we think of as the diene?
Rings. So are we talking about today's stuff where this diene will be a ring?
Yeah.
Yeah, we're going to talk. We can go over that. This was from last time.
Okay.
So we didn't do rings last time. We're going to do rings today. And the problem set that I put online was probably for today, and will be on Monday's quiz. So these were the first 2 rules. Rule number 1, S-cis. Rule number 2, stereochemistry of the alkene gets preserved in the product, gets transferred over to the product. Rule number 3 is the Endo-EXO rule. So the Endo-EXO rule only happens when you have a cyclic diene that is a ring. The cyclic diene means it's a ring. So let's make a fairly simple cyclic diene. This is called this is called cyclopentadiene. And it gets reacted with a cis alkene. So when you're reacting a cyclic diene with a cis alkene, there are 2 possible products of this reaction. So first, let's write the product of the reaction. So, 1, 2, 3, 4, 5, 6. So we're making, again, a 6-membered ring Double bond will go between carbons 2 and 3. Now, the reason that when we start out, I suggest maybe numbering is, then you can just figure out, okay, what are the groups that are attached to each one of those carbons. So in the diene case, I've got a CH2 that's attached to both carbon 1 and carbon 4. So what I would do is say, there's a CH2 attached to 1 and to 4, so I draw it like that. And then what's attached to carbons 5 and 6? The 2 CN groups. Okay, now notice I'm not showing stereochemistry yet. I'm going to show the stereochemistry that is possible in a minute. So that's just the structure of the molecule with no endo or exo. Okay. All right, everybody with me so far? So what does this ring look like? What is the 1 through 6 bicyclo ring look like? On its side, it looks like that, with carbon 1, 2, 3, 4, 5, and 6. So the CH2 group is a bridge. So last semester in my class, we talked about, numbering and naming the bicyclic ring systems. So this would be like a 2-2-1 in parentheses. It would be like a bicyclo 2-2-1 5-7 cycloheptane. And if that doesn't make sense, you don't have to worry about naming it. But these are 2 fused 5-membered rings together. So the CH2 would be called a bridge. Now, carbons 1 and 4 would be called bridge heads, and I'll come back to those in a minute or two. So this is what it would look like on its side. Okay. Now the question is, where do 5 and 6 go? Where do the CNs that are attached to 5 and 6? Because they could be equatorial or they can be axial. So if you just look at carbons 1 through 6, that is a boat-shaped cyclohexane ring. If you erase the CH2, it would be in the boat. The CH2 is holding those 6 carbons in the boat. And so you have equatorial and axial positions in all of those bonds. All of carbons 1 through 6 have an axial or an equatorial position, except carbon 1 and 4, where they're just sticking straight out. Okay. So there are 2 names for the 2 different kinds of stereochemistries. Number 1, the CNs have to be both equatorial or both axial because they are cis in the alkene. So let's see. Let's see what I do here. So what I'm going to do is this. I'm going to highlight this ring because that's going to be my point of reference. Okay, so I'm going to look at that 6-membered ring. Are the groups both above or both below the ring? What groups? My first group would be the CH2. So everything's going to be referenced to the CH2. When the CH2 group and the equatorial groups, those 2 positions, if I put the CN into those 2 positions, then that is what is called the EXO product. So when the bridge and the 2 groups are on the same side of the 6-membered ring plane, it's EXO. Let me redraw this so that I can color code it and then write the endo. So in this case, now I'm going to talk about the yellow positions where the bridge and the two groups are on opposite sides of that 6-membered ring. That would be called the endo product. Okay, so the technical definition of this is based on the bridge and where the two groups are. And if they're both on the same side of the ring, then it's exo. If they're on opposite sides, it's endo. That's the way those are actually defined. And sometimes it gets a little tricky because you have 3 propellers on there. So which 2 propellers make up the ring? Well, it's easy. In a Diels-Alder reaction, it's the 6-membered ring with the double bond, because the double bond is between carbons 2 and 3. Julia?
So if you originally had a trans alkene, is it then like impossible to have an exo-endo product?
Right. Endo and exo only apply as names to when the two groups are cis. So I'll do that in a minute. If it's a cyclic alkene with a trans diene, let me start all over again. If it is a cyclic diene with a trans alkene, there is no endo and exo. In that case, you would just have one above, one below. It doesn't matter. So that's the technical definition of what endo and exo is. Now, the way I think about endo and exo is, what I like to do is think about these molecules as sort of passing a cylinder through it. So if you think about having a cylinder that I would sit that molecule inside of, maybe I would have the cylinder that kind of looks like this. So that the bridge sits inside of the cylinder. So if you go to biology, right, we have exo and endo, exoskeleton, endoskeleton. Exoskeleton is skeleton that is outside, endo is inside. So if you've got that under control, then you can think of it as saying, okay, here's my cylinder, and in this case the groups are pointing outside the cylinder, they're directed outside, whereas here they're kind of in the cylinder, so that's exo and endo. That's another way to remember it. I think my PowerPoint notes had the exact definition, and I didn't use the entire ring as my plane of reference, but I think using the entire ring works better. So that's the difference between the endo and the exo. But you only get, and so then the question is, which one's the major product? It turns out if you do this reaction, you get 100% of the endo product. And that is the major product of the reaction. I don't know. I was under the misunderstanding that was the exo product was forbidden. But when I was revamping my version of the Diels-Alder reaction that we did this week, I found one where they said, well, if you raise the temperature up high, you'll get some exo product. So apparently it's not forbidden. It's just this is the endo product is the major product under most circumstances. You can always violate rules, except when things that are forbidden are usually forbidden. Why are they? That has to do with molecular orbital theory and Woodward-Hoffman rules and frontier molecular orbitals, which I'm going to say are beyond the scope of this course. They're in the molecular orbital theory is in your book, and I'm sure it talks about with Diels-Alder. We're not going to go there. We don't have the time, and if you want to learn about orbital theory, you can take physical chem. So the endo product is favored by those Woodward-Hoffman rules. And Woodward and Hoffman won the Nobel Prize for that. Robert Woodward. He was a huge synthetic chemist who, back in the 50s, was doing synthesis on total molecules that they found in nature. So I think I've shown you at some point the Taxol molecule. That would have been one in the time that his group would have tried to basically synthesize from scratch. The most notable thing about him is there's probably no pictures of him without a cigarette in his hand, because he was apparently a chain smoker. So I've never seen a picture of him with no cigarette in his hand. I'm sure he accepted the Nobel Prize puffing away. I have a picture in my office that was allegedly signed by him, but it has him with a cigarette in his hand. Rode Hoffman shows up occasionally on chemistry videos. He was a theoretical chemist, and he's a physical chemist, so he did that. He came to Cleveland a few years ago to give a talk down at Cleveland State. I gave a couple of the books I have that were written by him, more general science books, to one of my former colleagues, and she took them down and had them signed. Now, they were my books. He signed one to her, one to me. I lost ownership of the other book that was mine. But I still have one that says, "To Mike." So, but I didn't actually interact with him. But the whole idea of these orbitals are why these reactions go. And there's another thing we'll talk about here in a minute or two about electron donating and electron withdrawing groups, and the best way to make the reaction go. That's all rooted in frontier molecular orbital theory, which we're not going to talk about. Okay. So when we do this reaction, we're always going to get the endo product. Now, what if you're having troubles drawing the structures like I've drawn them in blue and yellow here? It's okay, because what we can do is we can take our molecule that I've drawn up here, and I can say, and I usually say, let's put in a bold wedge to the bridge. If you want to be opposite, you can put in a dashed wedge to the bridge. But remember that the bridge and in the endo product, the bridge and the groups I added must be opposite each other. So that means that the bonds to the CN groups have to be dashed. So if you have a bold bridge, you need a dashed set of groups. If you want a dashed bridge, you need a bold set of groups. But they have to be basically opposite or trans. Okay. So the two ways we can represent that product are by basically taking and using bold wedge here, dashed wedge here, or vice versa. Or if you're good, you can draw these kinds of structures and show that the two CN groups or the two groups are basically in the axial position. Either one. I've had a lot of practice with those, with the bicyclic systems. But either one would be acceptable. So the third rule then is the endo rule. Cyclic diene cis alkene always produces the endo product as the major product. Right. Is everybody with me? So then let me do the one. So then you might say, well, what would happen if the two CN groups were trans? Number one, you're not going to get an endo or exo product because endo and exo are defined with the two CN groups on the same positions. So if I'm going to react a trans alkene with a cyclic diene, I'm going to end up with a bold CH2 in this case, the bold bridge, meaning the bridge is pointing above the plane, and then one CN group would be bold and one would be dashed, and it doesn't matter which is which. That does not have a name. That is just the product. There's no endo or exo with that. Okay. And then that structure would look like this. One CN equatorial, one CN axial. Does that make sense to everybody? I mean, obviously, there's practice problems in Monday's quiz, but you can draw the structure either way. But again, EXO and Endo only refer to when the two groups are both equatorial or both axial. If it's one of each, it doesn't have a name. Any questions? Now, these bicyclic compounds look pretty bizarre, but they're not. This particular bicyclo 221 heptane would be the basis for a number of molecules that you could go out to one of these pine trees and pull a needle off, and there would be plenty of those kinds of compounds in them. Just a couple of them that are basically responsible for a pine smell would be if we had two methyl groups there, maybe one there, and a carbonyl. That's something like camphor. And if you replace the OH, whether it's axial or equatorial, you would have what's called borneol or isoborneol. And those all have a pine, they all contribute to the pine smell of pine needles. So these structures are not that bizarre. Plants are able to put these, do Diels alders, which I'll show you in a moment. Plants are able to do that, and they're able to form these cyclic systems. And if you analyze an essential oil, or which are used for perfumes and colognes and other fragrances, you would find lots of these sort of Diels alder products in that mixture. One other thing about these fused systems, and that is that when we've talked about carbocations, we've said that the hybridization of a carbocation is sp2, right? All three groups have to be planar. Back in the 60s, probably mid to late 60s, there was a question when people were looking at carbocations, does it always have to be trigonal bipyramidal? And so these are the perfect molecules to test that with. So what you do is you take and you basically synthesize the molecule, and you put a halogen or a leaving group there. And back in the 60s, everybody was interested in carbocations, and then they figured out most of what they needed to know, and then nobody's touched it since. But this would be a perfect system because those three carbons that are attached to a leaving group can never be trigonal planar because the fused system will not allow that. So if you were going to say, can I form a carbocation out of this? This would be the molecule to use. And so if I remember correctly, they used a fluorine, and they used an antimony compound that would rip the fluorine off. In the next couple of weeks, we'll talk about that in terms of adding to benzene rings. But let's say I put a chlorine there and I add silver to it. The silver would usually rip the chlorine off to form a carbocation because you'd form silver chloride and it would precipitate. In this system, you cannot form the carbocation at the bridge. They could not form the carbocation at the bridge. Now, they formed a carbocation, but what they found was that they did a hydrogen shift to form the carbocation over here at the non-bridge. So there is like a rule called Brett's rule that says the bridge carbon cannot be a carbocation. So that helped us in terms of determining the structures of carbocations. They must be trigonal planar. And I think, and somehow my PhD advisor was involved in that kind of stuff. In our group, we did calorimetry, so we measured heats of reaction. And somebody who, if he hasn't won the Nobel Prize, he will eventually, had sent one of these compounds with a fluorine, I believe, there. And I found a little tube of something in the lab, and I opened it up, and I'm like, wait, this is from, as his name is Paul von Rogschweier. And so I picked it up, and he did lithium chemistry, which is like what I did my PhD in. So I'm like, oh, there's a handwritten personal letter here from Paul Schleier about this stuff. And it was like, Ned, this is the world's supply of this. When you're done testing it, can you send it back to me? Okay, it was 1965 to 69. So I took it to him, and he's like, yeah, I don't think he needs it back now. So he sent him his world supply and never got sent back. I should have kept the letter. Then I'd have the letter of a Nobel Prize winner, but they were involved in that kind of stuff. So carbocation chemistry, that's George Olah, who was at the Case Technical, or the Western Reserve when it was called that. So he was there when he did a lot of his work to win the Nobel Prize there. So these systems are not as strange as they look. They are pretty much everywhere. So most people, when you think like, oh, plant chemistry, really? Plant biology, really? Right? But plant biology does some pretty interesting things. So plants are able to do Diels-Alder reactions like all day long. And what they do is they take molecules called isoprene, and they take two of these molecules and they react them together. So let me rewrite the structure here. And then let me take another isoprene molecule so that it does a self-Diels-Alder reaction. So a plant can take isoprene and it can turn it into basically what's called a terpenoid. So you can take this pair of electrons, move it here, form the bond there, form the bond there if we want 1, 2, 3, 4, 5, and 6, so we can keep track of this. And the molecule that we make is going to have the double bond between 2 and 3. And then on this side, it's going to have that molecule. And that's something that is going to be in probably most citrus flavored beverages, because that's going to be called limonene. So the way that oranges and limes and lemons are able to put that molecule together is by a Diels-Alder reaction. And they can take any of these isoprene molecules and they can make a variety of different terpenoids out of them. If you've heard you've heard maybe of turpentine that you use to clean paint brushes that have oil paint on them. There was a big thing back in the 90s, like infomercials late at night. I don't watch TV late at night, so I don't know if infomercials still exist. But they would, turpentine is kind of foul smelling. So they're like, well, don't strip your paint with turpentine, strip it with basically orange peel oil. So take the orange peel, crush it, take the oil, and it'll strip paint. Why? Because it's basically the same class of compound as turpentine. It just smells better. And if you took that citrus peel oil and you changed the different terpenoids around, you could get it to go from smelling like oranges to smelling like turpentine with just a few changes of a few different compound percentages. So plants do some interesting chemistry. And some of the interesting things they can do are these Diels-Alder reactions to put these molecules together. Because you could say, well, does it stop here? No, because I have double bonds in that molecule. I could then do a Diels-Alder on each one of those. The other thing about this is the molecule gets put together with a chiral center there. And there is a difference in smell between L-limonene and D-limonene. So the plants are able to somehow put these molecules together to achiral molecules and make a majority of one chiral molecule or the other. Which means the other things that are, the enzymes and stuff that are doing this are chiral themselves. So, you know, if you're like in plant biology and you're like bored, plants do cool things, at least organic chemistry wise. Probably won't convince you that it's exciting, but I guess to some people it is. So these are the building blocks for perfumes, essential oils, anything that has a fragrance. Those are going to be the molecules. And if plants can make them, then we use them. If there's something we have to make, then we make that as well. Okay. So those are that's the Diels-Alder. So those are the big three rules. So everybody still kind of with me? All right, the last thing that we'll kind of talk a little bit about more on Monday and into benzene ring chemistry is the following. That in your book, it says that the substituents attached to the diene and dienophile greatly influence the reaction rate and yield. All of this is rooted in frontier molecular orbital theory and what's called HOMO and LUMO theory, the highest occupied molecular orbital and the lowest unoccupied molecular orbital that you may have heard about in general chemistry back in a long time ago. But basically, HOMO-LUMO theory is how you can base the molecular orbitals, is how you can move electrons. It's the ultimate reason for color, for why some materials are colored, because they absorb ultraviolet or visible light. But in this case, changing the groups that are attached to the diene and the alkene will affect their rate. So as it says here, if I just took butadiene, which is the one we've been using without the ring, the two double bonds with no substituents, that's 1,3-butadiene. That's what we made in the lab this week after we cracked the sulfone. We made butadiene. Butadiene plus ethene is a pretty slow reaction, poor yields. So how do we optimize a Diels-Alder reaction? And you could say, well, yesterday for me, and some of you all week, what did we do? We reacted it with the maleic anhydride. So the best way to get the reaction to go is if the diene is electron rich and the dienophile, which means that is the alkene, is electron poor. So how do we make the diene electron rich and the alkene electron poor? What we do is we add electron donating and electron withdrawing groups to those. So now would be as appropriate a time to talk about electron donating and withdrawing groups, and not in the next 2 minutes, but I'll give you the basics, and then we'll go into a little bit more of this on Monday. But the electron donating and withdrawing groups, just to tell you what you're going to have to know in the next couple weeks, are used for benzene rings and the reactions of benzene rings. You will know 10 of them. You will know 10 electron donating and withdrawing groups. You will know them in order from most electron donating down to most electron withdrawing, because we have to know that with benzene rings. Here's the simplest case. Attach a halogen to a carbon atom. Better yet, attach a halogen to a double bond. What does that halogen do? It is going to withdraw electron density from the double bond. So it will be an electron withdrawing group. Pretty straightforward how that happens, right? Halogen is more electronegative than carbon, so what happens? The halogen becomes slightly negative and the carbon becomes slightly positive. How did it get that way? Because the halogen is more electronegative than the carbon. So it sucked a little bit of electron density out of the carbon. It did so through the sigma bond, through an electronegativity difference. So we're going to further classify that as what we would call an inductive effect. So we're going to call that the inductive way to withdraw electron density from a carbon. Use an atom that's more electronegative. Oh, here's an easy one. How do I push electron density into that double bond? What kind of group can I add to it?
Like an R group.
Any alkyl group. What happens there? The carbons become the hydrogens become slightly positive. The carbon becomes slightly negative. What does the slightly negative carbon do? It pushes the electron density into the double bond. I didn't ask you anything new here because the pushing of the electron density in the double bond explains what? The stability of the double bond. Why is a double bond that is more substituted more stable? Because double bonds like to get electron density pushed into them. What's the simplest group to push in? An alkyl group. So those two, pretty straightforward. This week we used a carbonyl group on our double bond, right? The maleic anhydride. It was an electron withdrawing group that made the double bond poor. But how would a double bond withdraw electron density? When you push and pull out of the sigma bond, that's called induction. There's a more powerful way to push and pull, and that's what's called resonance. And so that's where we'll pick up on Monday, along with the aromaticity is the other topic for Monday. All right, I'll send out a note on the quiz topics, but it will be writing some Diels-Alder reactions, probably with rings. If you have any questions, put them on Piazza or send me an email. Otherwise, we will have a quiz on Monday, and there's some extra, and I'll probably put a couple extra problems online for you to try for them.